start.
So in this particular set of slide, or in the first slide in this course of 4 movies explaining the basic theory of different experiments, I am presenting here some slides highlighting the background to sparse-pulsar sintering experiment. And first of all, I must say that sparse-pulsar sintering experiment, as I said before, is very useful to fabricate ultra-fine grained and nanostructured biomaterials. Now the question is, what is biomaterial nanocomposite? So this is the Koichi Nihara from Japan. He defined that nanocomposite in such a way that it can be intragranular nanocomposite when the nano-sized particulates are inside the grains. It can be intragranular first. Second one is the intergranular, that is when nano-sized particulates are residing at the grain boundaries. It can be intragranular when it is a mixture of both, and the fourth one is nano-nano when both the matrix and the particulates are nano-sized. Now, what are the major issues in the process of ceramic nanocomposites? The top one has been shown that cost-effective synthesis to obtain non-agglomerated nanocrystalline ceramic powder. The second one is the compaction nanoparticles without the formation of cracks and all. Third one is the inhibition of grain growth while achieving full density and force and retention of nanosized grains of particulates and dispersion nano reinforcements in the matrix. So in this context, sparse-pulsar sintering has been reported to be the most effective and widely used technique around the world in different research labs as well as in the industrial setting. So what is the major advantage of sparse-pulsar sintering? That one can get the heating rate of up to 600 degrees Celsius per minute, which is a huge heating rate if we compare with the traditional conventional furnaces which are typically used in the laboratory. So there one can get the heating rate of up to 2 to 10 degrees Celsius per minute as opposed to 150 or 200 to 600 degrees per minute what we can obtain in the sparse-pulsar sintering. So in view of the higher heating rate, sintering temperature is often lowered by 200 to 300 degrees Celsius, and typical holding time in sparse-pulsar sintering is 0 to 10 minutes. So therefore leading to the total processing time of less than half an hour. And the benefits is the reduced sintering time, good grain-to-grain bonding, and clean grain boundaries. So in this slide, I am showing that how the current is flowing through anode to cathode during the DC pulse. When DC pulse current is supplied to the graphite die punch assembly, and depending on the conductivity of the powder sample, that some fraction of the current will pass through the graphite die, some fraction will current to the graphite die powder compact also. And what is this SPS effect? That is nothing but the combination of simultaneous application of mechanical pressure and high power pulse source, and typically pulse source is 6 kiloampere, which is much higher than the welding current, and pulse direct current leads to the surface cleaning and surface activation of the powders and generation of electric discharge at the neck region. And in order to understand, we also carried out some MATLAB simulation to see that how the temperature profiles that are generated during the SPS. Now what you can see, these dotted lines in this slide is essentially denotes the boundary of the powder compact with the die wall, and then what we can see in this boundary by the powder compact die wall, that depending on the powder conductivity, one can get the red curve which shows for the samples with the lowest conductivity of 5 watts per meter Kelvin compared to the blue one, that is samples with the highest conductivity, that is 80 watts per meter per Kelvin. So it is very clear that in case of the powders with higher conductivity, this blue line shows a minimal thermal gradient in the powder compact. And subsequently, we have also performed some ABAQUS simulations to see that how these temperature profile or thermal conditions they look like during the actual SPS conditions. One can see that the highest temperature condition is always maintained or developed at the die punch assembly, where you can see that red regions, and this is essentially around more than 1000 Kelvin. See this 4-particle model where pressure is applied, and if you supply the current, then the diffusivity also would increase at the neck region.